Hello, and welcome to Tech with Shaping Pixel. This time we are bringing you free certification crash course. The AWS Certified CloudOps Engineer Associate Certification Exam, also known as SOA-C03, is designed for cloud operations engineers with at least 1 year of experience in deployment management, troubleshooting, networking, and security on Amazon Web Services. If you're not already subscribed, please subscribe to our YouTube channel. Thorough preparation will help you succeed and earn your AWS Certified CloudOps Engineer Associate credential. Review the official AWS exam guide for detailed task statements and domain weightings. This exam lasts 130 minutes and features 65 multiple choice or multiple response questions. Only 50 questions count toward your score, while 15 are unscored and used for evaluation. There is no penalty for guessing, so always answer every question. The passing score is 720 out of 1,000. The exam covers 5 domains: monitoring, logging, analysis, remediation, and performance optimization, reliability and business continuity, deployment, provisioning, and automation, security and compliance, and networking and content delivery. Each domain tests your skills in areas like configuring metrics with Amazon CloudWatch, implementing backup strategies with AWS Backup, automating deployments using CloudFormation and the AWS Cloud Development Kit, managing security with AWS Identity and Access Management, and optimizing networking with Amazon CloudFront and Route 53. Networking. Let's break down what a virtual private cloud, or VPC, really is. Imagine the Amazon Web Services, or AWS Cloud, as a massive digital space. Inside this space, your VPC is your own private, isolated section. When you create a VPC, only your AWS account can access it. No one else, not even other AWS customers, can see or interact with your VPC. There are millions of VPCs worldwide, but each one is completely separate. This isolation is key to keeping your resources secure. So, what do you actually do with the VPC? It's where you deploy resources like compute power, storage, databases, and networking tools. This setup lets you build and run your own solutions in the cloud, all within your secure environment. Setting up a VPC is straightforward. You give it a name and define an IP address range using something called a classless interdomain routing block, or CIDR block. By default, you can create up to 5 VPCs per region in your AWS account. In summary, a VPC is your secure, private slice of the AWS cloud, perfect for deploying resources safely. Next, we'll explore how to segment your VPC for even more flexibility. Let's break down virtual private clouds, or VPCs, and subnets in Amazon Web Services. Understanding these concepts is key to building secure, scalable, and resilient cloud infrastructure. A VPC is your own isolated network within AWS. When you create a VPC, you assign it a CIDR block, which defines its range of IP addresses. Subnets are segments within your VPC, each with their own CIDR block that fits inside the VPC's range. Subnets help organize resources and improve management. Subnets can be public or private. Public subnets connect to the internet through an internet gateway and the special route in their route table. Private subnets, like those for databases, have no route to the internet gateway and are isolated by default. Every subnet starts private until you add internet access. For high availability, spread your subnets across multiple AWS availability zones. This way, if one zone fails, your resources in other zones keep running, ensuring your services stay online and resilient. Each subnet reserves 5 IP addresses for networking and AWS functions. For example, in a subnet with 256 addresses, only 251 are usable for your resources. This ensures smooth network operations within your VPC. Security is crucial in Amazon Web Services, or AWS, especially when managing your virtual private cloud. One key component is the Network Access Control List, or NACL. NACLs act as virtual firewalls at the subnet level, controlling both incoming and outgoing traffic. Each subnet in your virtual private cloud automatically gets an NACL. By default, these lists allow all traffic, but for better security, you should configure them to only permit the traffic you want. NACLs use rules based on protocol, port range, source or destination, and an action to allow or deny. For example, a public subnet hosting web servers might have inbound rules allowing HTTP on port 80 and HTTPS on port 443 from any source. Any other traffic is denied by a default rule, ensuring only web traffic reaches your servers. It is important to remember that NACLs are stateless. This means you must explicitly allow both request and response traffic in your rules, as NACLs do not automatically track connections. In contrast, security groups in AWS control traffic at the instance level, not the subnet level. They provide another layer of security working alongside NACLs to protect your resources. Let us break down the difference between security groups and network access control lists, or NACLs, in cloud security. Both filter traffic, but they operate at different layers and serve unique purposes. NACLs, or network access control lists, work at the subnet level. Imagine 3 private subnets, each with its own IP address range. A single NACL can be associated with all 3, controlling which types of traffic are allowed in or out of the subnet. Security groups, on the other hand, operate at the instance level. For example, you might have a security group attached to your database instances. These groups specify which sources can access specific ports, like allowing only MySQL or Aurora traffic from a certain subnet. When a request is made, it first passes through the NACL at the subnet boundary. If allowed, it then reaches the security group attached to the instance. Only if both layers permit the traffic does it reach its destination. Otherwise, it is blocked. NACLs are stateless, meaning you must set rules for both inbound and outbound traffic. Security groups are stateful, so return traffic is automatically allowed. This layered approach enhances your cloud security. Let us break down the role of a NAT gateway in a virtual private cloud, or VPC. Imagine your VPC has 2 subnets, one public and one private. The private subnet is where your application servers, like EC2 instances, live. These servers need updates, but they cannot access the internet directly. To solve this, you place a NAT gateway in the public subnet. NAT stands for Network Address Translation. The NAT gateway gets a public IP address, called an elastic IP address, and connects to the internet through the Internet Gateway. You then update the private subnet's route table to send outbound internet requests to the NAT gateway. This way, your private EC2 instances can download updates or patches from the internet, but they remain hidden from direct inbound internet traffic. The NAT gateway only allows outbound connections from within your VPC. It blocks any inbound connections initiated from the internet, keeping your private subnet secure. AWS manages the NAT gateway for you, making setup simple and ensuring high availability. In short, a NAT gateway lets private subnets access the internet securely, while blocking unsolicited inbound traffic, helping you keep your EC2 instances updated and protected. Let us explore how to create private subnets with IPv6 using an egress-only internet gateway to maintain privacy while allowing outbound connectivity. Traditionally, with Internet Protocol version 4, or IPv4, private subnets are isolated from direct internet access. Resources in these subnets use a network address translation, or NAT, gateway to reach the internet. This setup ensures that connections can only be initiated from within the private subnet, and responses from the internet are allowed back in. However, unsolicited inbound connections from the internet are blocked, keeping the subnet private. With Internet Protocol version 6, or IPv6, every address is globally unique and publicly addressable. This presents a challenge. How do you keep an IPv6 instance private if all addresses are reachable from the internet? Simply placing an instance in a private subnet is not enough, since IPv6 does not use NAT in the same way as IPv4. To solve this, you use an egress-only internet gateway. This gateway allows outbound IPv6 traffic from your private subnet to the internet, but blocks any inbound connections initiated from the internet, preserving privacy for your resources. Remember to update your route tables, security groups, and network access control lists to ensure your IPv6 private subnet remains secure and functions as intended. A virtual private network, or VPN, is a secure way to connect two remote networks over the internet. In Amazon Web Services, or AWS, VPNs help link your virtual private cloud, or VPC, to your on-premise data center. Imagine your VPC in AWS and your data center, each with its own private network. You want resources in both locations to communicate securely. A VPN connection lets you do this, even if your VPC subnet is isolated from the internet. On the AWS side, you create a virtual private gateway and attach it to your VPC. In your data center, you set up a customer gateway, which can be hardware or software. These gateways form the endpoints of your VPN tunnel. You update your route tables so AWS resources know how to reach your data center. Security groups must allow the right protocols, like SSH or remote desktop, from your data center's network to your AWS instances. Direct Connect is another way to link your data center to AWS, but it does not use the internet. Instead, it uses dedicated private infrastructure for a more secure and reliable connection. Your data center connects to a Direct Connect location, which bridges to AWS. This setup allows access to both private VPC resources and public AWS services, all without traversing the public internet. Direct Connect offers speeds up to 10 gigabits per second. Virtual Private Cloud Peering, or VPC peering, is a way to connect two VPCs so their resources can communicate securely. Unlike VPN connectivity or Direct Connect, which link your on-premises network to a VPC, VPC peering connects VPCs directly. Each VPC might contain resources like EC2 instances or databases. With VPC peering, these resources can talk to each other, even if the VPCs are in different regions. The peering connection itself is hosted on Amazon Web Services infrastructure, making it highly resilient with no single point of failure or bandwidth bottleneck. VPC peering is always a one-to-one connection. If you have 3 VPCs, each pair that needs to communicate must have its own peering connection. Also, VPCs cannot have overlapping IP address ranges. For example, if both VPCs use 10.0.0.0/16, pairing is not possible. To set up peering, the owner of one VPC sends a request to another. If accepted, both VPCs update their route tables to allow traffic between them, ensuring their CIDR blocks do not overlap. Finally, update your security groups to permit the right resources, ports, and protocols. That's VPC pairing, a simple, resilient way to connect VPCs for secure communication. Navigating networking in Amazon Web Services, or AWS, can be complex. From route tables to CIDR blocks, connecting virtual private clouds, or VPCs, is essential for building secure cloud environments. While VPC peering and VPN connections are common, managing dozens or hundreds of connections quickly becomes overwhelming. Each new VPC or on-premises network adds complexity, making traditional methods hard to scale and maintain. Enter AWS Transit Gateway, Amazon's managed network transit hub. It acts as a regional router, allowing you to interconnect hundreds of VPCs and on-premises networks without the hassle of maintaining countless peering or VPN connections. Transit Gateway uses attachments to connect VPCs, VPNs, and direct connect gateways. Each attachment serves as a source and destination for traffic. Route tables within the Transit Gateway direct packets based on destination IP addresses, enabling flexible and secure network topologies. Transit Gateway scales automatically, supports multiple route tables, and simplifies adding new networks. However, there are limits: 5 transit gateways per region, 5 attachments per VPC, and bandwidth caps. Still, it's a powerful solution for complex AWS networking needs. Elastic IP addresses, or EIPs, are a key part of managing network infrastructure in Amazon Web Services, or AWS. While public IP addresses can be assigned to instances, they are not persistent and will change if the instance is stopped or terminated. An elastic IP address is a persistent public IPv4 address that you can allocate to your AWS account. Unlike standard public IP addresses, an EIP remains associated with your account until you choose to release it. This means you can attach it to any instance or Elastic Network Interface, or ENI, as needed. If you associate an EIP with an instance, it replaces any existing public IP address. The EIP will remain with the instance even if you stop and start it, ensuring continuity. However, if an EIP is not attached to a running instance, AWS will charge you for it. Always release unused EIPs to avoid unnecessary costs. In practice, associating an EIP is simple. Allocate the address, attach it to your instance, and it instantly replaces the previous public IP. Disassociating and releasing the EIP is just as straightforward. Elastic IP addresses provide persistence and flexibility, but remember to manage them wisely to avoid extra charges. Elastic Network Interfaces, or ENIs, are virtual network cards you can create and manage within your virtual private cloud, or VPC. ENIs let you add flexible networking options to your Amazon EC2 instances, making your cloud environment more adaptable. Every EC2 instance starts with a primary network interface called ETH0, which cannot be removed. However, sometimes you need more than one interface. For example, you might want to separate management traffic from production traffic by adding a secondary ENI. To do this, you can create a new ENI in the AWS Management Console. Assign it to a different subnet, like a management subnet, and attach it to your instance. The ENI's configuration, such as its IP address and security group, keeps its configuration even if you detach and reattach it to another instance. Detaching or deleting an ENI is simple. Just select the interface, choose Detach, confirm, and then delete if it is no longer needed. The ENI's configuration always stays with it. ENIs provide flexibility for your networking needs. Remember, the number of ENIs you can attach depends on your EC2 instance type. Check AWS documentation for details. If you want to boost your Amazon EC2 instance's network performance, enabling enhanced networking with the Elastic Network Adapter, or ENA, is the way to go. Let's explore how ENA can help your workloads. The Elastic Network Adapter is a custom network interface designed to optimize network speeds for EC2 instances. With ENA, you can achieve network speeds of up to 100 gigabits per second for supported Linux compute instances. Enhanced networking also delivers higher bandwidth, increased packets per second performance, and best of all, it comes at no extra cost. To use ENA, your instance must be one of the supported types and run a compatible Linux kernel version, such as 2.6.32 or 3.2 and above. If you launch an instance using Amazon Linux 2 or the latest Amazon Linux AMI on a supported instance type, enhanced networking is enabled by default. For the most current list of supported EC2 types, check the AWS documentation. To confirm ENA is active, ensure the ENA module is installed and the ENA support attribute is set. Run modinfo ENA in your terminal and use the AWS command line interface to check ENA support. With ENA, your EC2 instances can reach new levels of network performance simply and efficiently. VPC endpoints let you privately access Amazon Web Services or AWS services using the AWS internal network instead of the public internet. This means you do not need to set up an internet gateway, NAT gateway, virtual private network, or direct connect. There are two types of VPC endpoints: interface endpoints and gateway endpoints. Each type connects your virtual private cloud, or VPC, to AWS services in a different way, providing flexibility and security for your cloud resources. Interface endpoints are elastic network interfaces, or ENIs, placed within your subnet. They use private link to create secure private connections between your VPC, AWS services, and even on-premises applications. Communication must start from your VPC, not the service. Gateway endpoints are targets in your route tables, allowing access to supported services like Amazon S3 and DynamoDB. When you create a gateway endpoint, selected route tables are automatically updated to route traffic through the endpoint. Gateway endpoints only support IPv4. When you create an interface endpoint, AWS automatically creates a private DNS hostname in your VPC. Applications using the default DNS name will seamlessly connect through the internal AWS network with no need for reconfiguration. Everything stays private and secure. Let's spotlight a powerful tool in your Amazon Web Services toolbox, the VPC Reachability Analyzer. Whether you are new to cloud computing or an experienced user, this feature can save you time and frustration. In the past, diagnosing connectivity issues in Amazon Web Services could be overwhelming. Forgetting a security group rule or missing an internet gateway often left users stuck searching for answers. The VPC Reachability Analyzer changes that by making network troubleshooting much simpler. The VPC Reachability Analyzer tests connectivity between 2 points in your architecture. It checks each network component along the path, from security groups and elastic network interfaces to network access control lists. At the end, it provides a detailed report highlighting any issues it finds. For example, if you want to check connectivity between two instances, just select them, Choose your protocol like TCP or UDP and run the analysis. If there's a problem, the tool points out exactly where the connection fails, such as missing inbound rules. This tool supports many endpoints, including VPN gateways and VPC peering connections. For just 10 cents per run, it's a smart way to keep your cloud network running smoothly. Troubleshooting connectivity between Amazon EC2 instances can get complicated as your network grows. Today, let's see how to quickly diagnose connection issues between two instances in the same virtual private cloud, or VPC, using the VPC Reachability Analyzer. First, identify your source and destination instances. For this example, we'll test connectivity from instance 1 to instance 3, both inside VPC 1. Open the VPC Reachability Analyzer, create a new analysis, and select instance 1 as the source and instance 3 as the destination. Since we want to test Secure Shell or SSH connectivity, set the port to 22 for both source and destination. Start the analysis. In just a few seconds, the tool will show whether the connection is possible. If the result says not reachable, click the Analysis ID to view details. The tool displays a network path diagram. In this case, it highlights that none of the security group ingress rules allow the traffic, blocking the connection. Edit the security group for instance 3 to add an inbound rule for SSH. Save the changes, then rerun the analysis. This time, the result shows reachable, confirming the issue is resolved. That's how you troubleshoot EC2 connectivity with VPC Reachability Analyzer. Let us explore how the VPC Reachability Analyzer can help troubleshoot connectivity issues between two virtual private clouds, or VPCs, in Amazon Web Services. This tool is essential for diagnosing routing problems, especially when using VPC peering connections. Imagine you have two VPCs, VPC1 and VPC2, connected by an active peering connection. You want to test if an instance in VPC2 can reach a web server running on port 80 in VPC1. Using the Reachability Analyzer, you set the source as VPC2 instance 1 and the destination as VPC1 instance 2. After running the analysis, you receive a not reachable error. Investigating further, you discover the route table in VPC2 does not have a route to the peering connection. The analyzer highlights this issue, showing the traffic path and pinpointing the missing route as the problem. To resolve this, you add the correct routes in both VPC's route tables, ensuring traffic can flow in both directions through the peering connection. Rerunning the analysis and conclusion. Rerunning the analyzer now shows the connection is reachable. The VPC Reachability Analyzer quickly identifies and helps fix network issues, saving valuable troubleshooting time. AWS Resource Access Manager, or RAM, is a powerful tool that lets you share a wide range of AWS resources from centralized accounts. With RAM, you can share resources like Aurora database clusters, dedicated hosts, resource groups, and especially virtual private cloud subnets. To get started with RAM, the first step is to enable sharing. You can do this through the Resource Access Manager console or by using the AWS command line interface. Once sharing is enabled, you create a resource share. This involves naming your share and selecting the resources you want to share. For example, you might create a share called DevTeam1 and include 3 subnets from the same virtual private cloud. Next, you assign permissions to your resource share. These permissions control what actions other users, called principals, can perform on the shared resources. If you choose to share with an organizational unit, or OU, All AWS accounts in that unit, including any added in the future, will have access. Finally, complete the wizard. The shared resources, such as the 3 subnets, will quickly appear in the virtual private cloud console of the selected AWS accounts, making collaboration seamless and efficient. AWS Global Accelerator is a global service designed to speed up and secure your application traffic. By leveraging the AWS Global Infrastructure, it routes user requests more reliably than the public internet, reducing latency and improving security for both UDP and TCP traffic. When you set up AWS Global Accelerator, you receive 2 static Internet Protocol version 4 or IPv4 addresses linked to a domain name system or DNS name. These addresses act as fixed entry points for your users, directing traffic to your application endpoints, which can be load balancers, EC2 instances, or elastic IP addresses. The accelerator intelligently routes requests through the optimal AWS edge locations, ensuring low latency and high availability. To configure AWS Global Accelerator, start by creating an accelerator and choosing your IP addresses. Next, add listeners to specify protocols and ports. Then create endpoint groups for each region. You can set traffic dials to control distribution and configure health checks to monitor endpoint health. Finally, register your application endpoints and assign traffic weights as needed. With AWS Global Accelerator, you can easily add or change endpoints across regions without updating DNS or static IP addresses, making it simple to scale and maintain high availability for your applications. Amazon Route 53 is a powerful global service from Amazon Web Services, or AWS, designed to help you register and manage domain names. It goes far beyond basic domain registration, offering robust tools for worldwide domain management. With Route 53, you can register domain names and manage the domain name system, or DNS, for your resources. The service routes internet traffic to your domain's resources and checks their availability using health checks. Route 53 leverages AWS's global infrastructure, using edge locations for high availability and redundancy. In fact, AWS offers a 100% available service level agreement for Route 53 thanks to its distributed DNS system. Route 53 lets you define how internet traffic is routed to your resources using various routing policies, such as failover and latency routing. The traffic flow feature enables you to create complex routing configurations by combining multiple policies for optimal performance. Route 53's application recovery controller manages failovers with integrated health checks. The Route 53 Resolver service connects DNS queries between your virtual private clouds and data centers, while the Resolver DNS firewall protects DNS queries within your VPC. Route 53 is ideal for architects, developers, system operators, and administrators seeking advanced domain management on AWS. It also supports certification exam objectives for AWS Solutions Architect and SysOps Administrator roles. Amazon Route 53 is the domain name management service from Amazon Web Services, or AWS. It acts like the Internet's phone book, translating easy-to-remember domain names into the numerical IP addresses that computers use to communicate. When you register a domain with Route 53, it becomes the authoritative domain name system, or DNS, server for your domain. Route 53 creates a public hosted zone for internet traffic, and you can also set up private hosted zones for internal networks called virtual private clouds, or VPCs. Each hosted zone includes essential records, 4 name server or NS records, and 1 start of authority or SOA record. NS records identify the DNS servers for your domain, while the SOA record defines the authoritative DNS server for your DNS zone. Route 53 supports standard DNS records, A records for IPv4 addresses, AAAA records for IPv6, MX records for email servers, TXT records for text information, and CNAME records to map one host name to another. Unique to Route 53, alias records let you map custom domain names directly to AWS resources, like CloudFront distributions, Amazon S3 buckets, or Elastic load balancers. When creating records, you set the name, type, value, time to live, and routing policy, which controls how DNS queries are answered. Amazon Route 53 health checks are powerful tools that help ensure your applications remain available and reliable. These independent resources work with most routing policies, allowing you to monitor the health of your endpoints and respond quickly to issues. When you set up a health check, Route 53 sends requests to your endpoint every 30 seconds. Based on the responses, Route 53 determines if the endpoint is healthy or unhealthy. This information guides how Route 53 answers DNS queries, always favoring healthy endpoints and ignoring those marked as unhealthy. You can configure health checks for different tiers of your application, verifying each layer before considering the entire application healthy. Route 53 adds up the number of healthy checks and compares it to a threshold you set. Health checks can target IP addresses or domain names using TCP, HTTP, or HTTPS protocols. For HTTP-based checks, you can even specify a string that must appear in the response body. Route 53 health checks can monitor the state of an Amazon CloudWatch alarm. The health status updates automatically based on the alarm's state, offering flexible options for handling insufficient data. Health checks are performed globally, and you can customize which regions are used. You can also choose to receive notifications whenever a health check fails, keeping you informed at all times. DMS routing policies determine how queries are answered. The simple routing policy links a domain name to one or more IP addresses, randomly selecting which to use. However, it does not support health checks. Weighted routing is similar, but lets you assign a numerical weight to each IP address, favoring some over others. A weight of 0 means a record is never returned. Weighted routing supports health checks, ensuring only healthy records are chosen. Geolocation routing tags records by location, such as country or continent, and returns the IP address best suited for the user's region. This helps serve customers in different languages or regions and can enforce licensing restrictions. Geoproximity routing, which requires Route 53's traffic flow feature, routes traffic based on distance and a bias value, allowing you to shift more or less traffic to specific endpoints by adjusting the bias. Failover routing directs traffic to a primary resource, but if a health check fails, it automatically redirects to a secondary resource. Latency routing chooses the record with the lowest latency for the user based on AWS's latency database, ensuring faster connections. Multi-value answer routing returns up to 8 healthy IP addresses for a single query, improving reliability. Each DNS routing policy offers unique ways to manage traffic, optimize performance, and ensure users reach healthy, responsive resources. Managing records in large, complex configurations can be challenging, especially when you have a group of resources like a fleet of web servers all serving the same domain. Traffic Flow is designed to simplify this process, making record creation and maintenance much easier. With the Traffic Flow Visual Editor, you can build complex sets of records and instantly see how they relate to each other. This tool allows you to combine multiple routing policies and health checks within a single configuration known as a traffic policy. Each traffic policy is automatically versioned, so you never have to start from scratch when making changes. Previous versions remain available until you choose to delete them, giving you flexibility and control over your configurations. A single traffic policy can define hundreds of records, and Traffic Flow generates all of them automatically when you create a policy record. You associate these policy records with domain or subdomain name records, and they appear in your hosted zone's record list. The same traffic policy can be reused across multiple public hosted zones, which is especially helpful when managing the same hosts for several domains. It is important to note that the geoproximity routing policy is only available if you use traffic flow, adding another layer of advanced routing options for your configurations. Amazon Route 53 Resolver is the Domain Name System, or DNS, service designed for your virtual private clouds, or VPCs, in AWS. It seamlessly integrates with your on-premises data center, making DNS management across environments straightforward and secure. To connect your data center's DNS with AWS, you need either a direct connect, often called DX, or a virtual private network, or VPN, connection. Once connected, you configure endpoints by assigning IP addresses in each subnet that requires Route 53 Resolver access. Route 53 Resolver manages both inbound and outbound DNS queries. Inbound queries let your data center resolve domains hosted in AWS. For outbound queries, you set up conditional forwarding rules. These rules specify which domains, hosted in your data center, should be forwarded from AWS. This setup ensures that DNS queries between your VPCs and your data center are handled efficiently and securely. The Route 53 Resolver DNS Firewall is a managed service that inspects and filters DNS queries originating from your VPCs. You define firewall rule groups, listing domains to monitor and actions to take. You can allow, alert, or block queries, and apply these rules to protect your VPC's outgoing DNS traffic. Amazon Route 53 Application Recovery Controller is designed to help you keep your applications resilient. It continuously monitors your application's ability to recover from failures and manages recovery across multiple availability zones, regions, and even your own data centers. With Route 53 Application Recovery Controller, you can define readiness checks to monitor AWS resource configurations, capacity, and network routing policies. These checks cover resources like auto-scaling groups, Amazon EC2 instances, Amazon Elastic Block Store volumes, Elastic Load Balancers, Amazon Relational Database Service instances, and DynamoDB tables. Readiness checks ensure your recovery environment is always prepared to take over when needed, verifying that capacity and scaling setups are consistent across regions before any failover. Readiness checks work alongside routing controls, which let you fail over an entire application based on custom conditions such as application metrics, partial failures, increased error rates, or latency. You can also initiate failover manually. Routing controls allow you to shift traffic for maintenance or during real failure scenarios, and safety rules help prevent failover to unprepared replicas. A control panel groups routing controls for your application, letting you turn traffic flow on or off to specific regions or availability zones. This enables custom traffic redirection during failover or maintenance. With fine-grained failover and verification, Amazon Route 53 Application Recovery Controller supports applications that demand very high availability. Amazon CloudFront is a content delivery network from Amazon Web Services, or AWS, designed to deliver your website's content to users worldwide with low latency and high speed. Its main role is caching content closer to your users. CloudFront uses a global network of edge locations to cache both static and dynamic content. For example, static files in Amazon Simple Storage Service, or S3, and dynamic content from Amazon Elastic Compute Cloud, or AC2, or Lambda functions, are distributed efficiently. To use CloudFront, you create a distribution and select your content's origin, such as an S3 bucket or an application load balancer. You can customize protocols, cache settings, price classes, and even use your own domain name with a digital certificate. CloudFront uses 3 caching layers: edge locations, regional edge caches, and AWS Origin Shield. This multi-layered approach improves cache hit ratios, reduces load on your origin servers, and enhances network performance by keeping content closer to users. CloudFront offers robust security, including encrypted solid-state drives, signed URLs, AWS Web Application Firewall or WAF, geo-restrictions, and integration with AWS Identity and Access Management. Monitoring is available through Amazon CloudWatch, AWS CloudTrail, and real-time logs. CloudFront is Amazon Web Services Content Delivery Network, or CDN, designed to cache and secure your content for faster, safer access worldwide. Let's look at 2 common patterns for using CloudFront to boost performance and security. First, you can set up CloudFront with an application load balancer as the origin. This means CloudFront sits in front of your website, caching content and protecting your backend. To secure access, configure CloudFront to add a custom HTTP header to each request. Then, set your load balancer to only forward requests containing this header, returning a 403 error for others. Rotate your custom header regularly to maintain security. Update your Route 53 DNS records so your website's friendly name points to CloudFront, not directly to the load balancer. Second, use CloudFront with an Amazon S3 bucket for static website hosting. CloudFront caches content globally, reducing latency. To secure access, create an Origin Access Identity, or OAI, and update your S3 bucket policy so only CloudFront can retrieve content. Use AWS Certificate Manager, or ACM, to enable HTTPS, ensuring secure delivery. With CloudFront, you can cache content closer to users and secure your backend, whether you use an application load balancer or S3. That's all in this video. Let's see you in the next part. If you're not already subscribed, please subscribe to our YouTube channel. Thanks. For all the latest real exam question and answers and more content, please visit our website, www.shapingpixel.com.